Okay, someone asked if we could look at some of these homework problems. I just fixed the one you told me about with the ethane. Okay, Ivy Lynn. Your middle name's not Lynn, right?
Number 7.
Number 7. So, actually, let's...
Oh, the green.
And I was working on your lab before class, hence being in the lab. And homework, this is number 7, right? You guys can't see yet. Okay. A student is told to use 20 grams of sodium chloride to make an aqueous solution that has a concentration of 10 grams per liter. Assume that 20 grams of sodium chloride has a volume of 7.50 milliliters. So show that she will need about 1.99 liters of water to make the solution. To make the solution, should she add the solute to the solvent or the solvent to the solute? So we have 2 questions. Start with the hard part, and that is the math. So she's told to use 20 grams of sodium chloride. So we have the mass of NaCl is equal to 20.0 grams. And it says assume that that gives us a volume of 10.0 grams, or excuse me, 7.50 milliliters. And then we want to see how much water she needs to get a concentration Now notice this is not a molarity, it is a grams per liter. .0 grams per liter. So what does the concentration mean? What is that measuring? Okay, so this is going to be, since it's in grams per liter, that's going to be the mass of solute divided by the volume of what? Of solution. And what we're trying to calculate is the volume of solvent. So volume of solvent was not part of that. Which one of these two has volume of solvent in it?
What was the question?
Which of these two things that are in the concentration contains the volume of the solvent as part of it?
The solution?
The volume of solution, because solution is solvent plus solute. So I'm going to have volume of solution is equal to the volume of solvent, what I'm looking for, plus the volume of solute. So I just plug that in, and I'm going to make my life easier, the solvent is water, so I'm going to put VH2O, and the solute is sodium chloride, so I'm going to use those subscripts. So the mass of my solute was the mass of NaCl divided by the volume of H2O plus volume of NaCl. Now I actually know all of the numbers but one in this equation because we started with the mass of sodium chloride we know is 20 grams. And the volume for our sodium chloride is 7.50 milliliters. So all I have to do now is say my concentration, 10.0 grams per liter, is equal to the mass of my sodium chloride, which was 20.0 grams, divided by the unknown volume of water plus the volume of the sodium chloride, 7.50 milliliters. There's only one thing I don't know in this equation. I do want to do one thing to be careful, units. Notice on the left-hand side, I had 10 grams per liter. On the right-hand side, I had 20 grams, grams of the same unit, volume of water, no units assigned to it yet, plus 7.50 milliliters. I'll want to convert that to liters so I have consistent units. But now I just need to solve this. Now, I don't know how astute you are with math. Everyone's going to be a little different. But when I have A equals B over C, to get C, I need to do two things. I need to multiply both sides by C and divide both sides by A. So then my C's cancel over here and my A's cancel over here. Effectively, what did I do? Effectively, I swapped the positions of C and A. And so we get what I'm sure Gabby said. That is, I have volume of H2O plus, and now I'm shifting units. So what does milli mean? 7.50 milliliters. What does milli mean? 1,000th, actually. And so that's 7.50 over 1,000, or 0.00750 liters, is equal to 20.0 grams over 10.0 grams per liter. 20 divided by 10 is not a hard number. That's 2. So I have my volume of water plus 0.00750 liters is equal to 2.00 liters. There's one last mathematical step. What's that last step? So I have volume of H2O is equal to, if I subtract that out, that's going to be 1.9925 liters, but I only have out to the hundredths place for my volume. And so I'm going to truncate this, actually round it to the same decimal point that I had for the total volume. And there I have my answer. So this was utilizing what we actually learned in, actually this could have been from an earlier chapter now, couldn't it? It probably was. It tells you at the beginning of the problem which chapter it is. But this was utilizing simply the definition of concentration. Everything after that was just math. Just math for somebody who's a physics professor is very simple. I understand for you it's not as simple as it is for me. So, that's why we go through it and we have these. So any questions about that part of the solution? Nope. Okay, then there's a second part to the question. Should she add the solute to the solvent or the solvent to the solute? There's a simple rule we always follow. Leslie, what's that simple rule?
Oh, guys. Okay. You always do the solute to solvent. And maybe I have that confused backwards or whatever.
You always add the solute to the solvent. So that was an always answer. In that case, she's going to add the sodium chloride to the water, not water to sodium chloride. Okay, let's, we can look at one more maybe. Do we have another homework question somebody wanted to look at? 12? Okay, so let's go back and see what number 12 is. I should tell you, my office hours are slightly different now. You might know that one of our teachers had surgery for cancer on Monday, and so I'm covering her class that goes from 2 to 3, so I won't be in my office from 2 to 3 if you come then for office hours. Just should let you know in case somebody's coming for homework help then. So problem number 12, a 16-gram sample of methane, CH4, and I forgot to subscript the 4 there, it looks like, another mistake. I mean, obviously, not just it looks like, is combined with a 16-gram sample of molecular oxygen in a sealed container. Upon ignition, what is a maximum amount of carbon dioxide that can be formed? And we have the reaction. So this is a type of problem like I worked through in class, and then people asked, could that be on the test? And I said, yes. You remember that? So this is an example like what I did in class. So we look at this relationship. Now, one thing I want to correct, because on a potential test question, somebody asked this. They said, you know, in this equation, how many moles of O2 do we have? That number 2 doesn't mean we have 2 moles of O2. It's a proportion. So for every mole of methane, we'll have 2 moles of oxygen, or we'll need to have 2 moles of oxygen. But we could have half a mole of methane and 1 mole of oxygen, and it works out. But we need to first calculate which reagent is our limiting reagent. So to calculate which one's our limiting reagent, we'll start by calculating how many moles of each reagent, the reagent of reactants here, the 2 chemicals we're starting with. How many moles of each one do I have? So we have methane, 16 grams of it. If I want to find how many moles, how do I go from mass to moles? So I get the molecular mass for CH4. So that's going to be the mass of 1 carbon plus the mass of how many hydrogens? So then for this level of class, we just look back there and we say, well, carbon is 12, because that's the number it says in the top right-hand corner for carbon. Is top right-hand, or I can't see. Is it top right-hand or bottom center? Bottom center, isn't it? Top right-hand 6, bottom center is 12. Is that right? Yeah. So we're just going to put 12 grams for the carbon plus 4 times, and hydrogen is 1. And so that's 16 grams. So if there's 16 grams in a mole, and I have 16 grams, how many moles do I have? 1. Because the number of moles, N is the symbol we use for moles, is going to be the mass divided by the mass for a single mole. So these should have been per mole. Equals 1 mole. So we have 1 mole of methane. Then we look at the oxygen. Also 16 grams. The mass for oxygen, how many oxygens are in an oxygen molecule? 2, because it's O subscript 2. So I'm going to have 2 times the mass of oxygen, 2 times, and Ivy's been looking back there. What is the mass for oxygen? For our purposes, that's 16.
Okay.
16 grams per mole. And so that's 32 grams per mole. So the number of moles of oxygen is equal to the mass of oxygen over the mass for a molecule of oxygen, or mole actually. So that's 16 grams over 32 grams per mole. 16 over 32 is 1/2. So we have 0.5 moles of oxygen. So now we look at our reaction to figure out which one is going to limit our reaction. We need 2 moles of oxygen for every 1 mole of methane we use. We have 1 mole of methane. How many moles of oxygen would we have to use all of the methane? We'd have to have 2 because we use 2 moles for every 1 simply based on the numbers out front. If there's no number in front, that means that it's a 1. Well, we don't have 2 moles of oxygen. We only have 1/2 mole of oxygen. So that means we can't use up all of the methane. How much of the methane can we use? If it was 1-to-1, since we have 1/2 mole of oxygen, then we'd be using 1/2. But it's not 1-to-1, it's 1-to-2. A quarter. So we can only use a quarter of the methane. Or a quarter of a mole, I should say. It is 1 mole, so it still turns out right, but we can only use a quarter mole of methane. Now, if we have 1/4 mole of methane added to 1/2 mole of oxygen, how many moles of carbon dioxide are we going to make? Just look at the prefix and multiply by. We started with 1/4 of these numbers. So what's the prefix here for carbon dioxide? 1. So if we have 1/4 for all of our prefixes, we're going to have 1/4 times 1 is a quarter. So we're going to end up with the number of moles of CO2 is equal to 0.25 moles. And what about water? How many moles of water is going to be produced if we have only 1/4 of a mole of methane that we can use? One-half, because we have times 2. And so the number of moles of water is equal to 1/2 a mole. And now we have all the information to answer our question. Upon ignition, what is the maximum amount of carbon dioxide that can be formed? So the carbon dioxide, it's 1/4 of a mole. And I'm guessing we want the answer in mass. It does not say in mass. So 1/4 of a mole would be a correct answer since it doesn't say what's the mass of it. But I'm going to shift back to mass because that's what we started with. So what is the mass for carbon dioxide? What would my calculation be to find the mass for 1 mole of carbon dioxide, the mass per mole of carbon dioxide? It'd be the same as we did in green up above, except for now, instead of methane or in orange, we had oxygen, we're going to have carbon dioxide. So using that method, what will I have? Okay, I'll have the mass for mole of carbon let me put 1 times plus what? plus 2 times the mass of oxygen. That's right. So that would be equal to 12 grams per mole plus 2 times 16 grams per mole is equal to 44 grams per mole. So if we're making 1/4 of a mole and it's 44 grams per mole, I just multiply what? The T. Oh, okay. The mass of the product. I have my subscripts because we have the molecular mass. Usually we just use a capital M for the molecular mass and a lowercase m for the total mass. And that's going to be really confusing, especially when I'm using handwriting. It's not very clean. I'm saying the mass of my product, which is carbon dioxide. So 0.25 is 1/4. 44 divided by 4 is 11. So we're going to have 11 grams of carbon dioxide that are formed. Now, if you look at our starting, we started with 32 grams of material. We have 11 grams of carbon dioxide. Where's the other mass go? Okay, well, some of it's going to be water, and some of it is still going to be methane because we had a surplus of methane. So we're going to end up with water and methane and carbon dioxide. Now, in your automobile, you're burning gasoline. What's gasoline? Don't really know, do you? Gasoline is a mixture of carbon chains. We're going to learn in today's class about carbon chains. So you have things like, well, ethanol is one of the things that we talk about. So let's look at what ethanol is. Ethanol means that it's carbon bound to a carbon. That's what the ETH part of ethanol means. And then it has an oxygen and hydrogen at one side. That's the all part. That's what makes something an alcohol. And how many bonds does carbon make? When we talked about its valence, we looked at carbon, we said, the first column there has a valence of 1. The second column has a valence of 2. Jump over to the column that starts with boron that has a valence of 3. Carbon's going to have a valence of 4. So how many bonds is it going to make? It's actually going to make 4. 1 for each of those valence electrons. It makes the number of bonds that will make it have a complete shell. It has 4, so it needs 4 more electrons to get to 8. So it's going to make a total of 4 bonds. So it's going to have 2 more bonds. And those bonds for ethanol are H and H. This carbon here only has 1 bond. How many more is it going to have to make? 3. So it's going to have 3 bonds to H. So that's what ethanol is. So when you have ethanol in your engine or in your fuel, that's what it is. Well, another thing we talk about in our gasoline is the octane. Now, octane does not mean how much octane does it have. But octane is a molecule. What do you suppose oct means? 8. So octane is a chain that has 8 carbons. And each of those carbons is going to have 3 total bonds. So this one's going to have 3 hydrogens. This one has 2 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 hydrogens. You can see that we get tired of writing these very quickly. So when we will learn in a few moments that we don't write it all out like this because it's too many things to write. So that's an octane. When you burn it, because that's what your car's doing, is burning it, you're burning octane and other chains like this. So that's C8H. How many H's? Well, there's going to be 2 for every carbon plus 2. So 2 times 8 is 16 plus 2 is 20. Oh, what does this yield? Well, ideally, we're going to yield water. And we're going to yield carbon dioxide. How do you balance this equation? The first thing, what was that?
Carbon.
Okay, the first thing is the carbon. We have 8 carbons here. So since we have one of these, we're going to have 8. And then we balanced our carbons. Now the hydrogens, we had 20 hydrogens, so how many water molecules do we need? We're going to have 10 water molecules. And then finally, on the right-hand side, we have how many oxygens? Actually, 8 times 2 is 16, plus 10 is, so we have 26 oxygens, so that means how many O2s do I need here? So there we've balanced the equation for burning octane. If it burns perfectly, what is it producing? Carbon dioxide and water. What comes out of the tailpipe of your car? When you see a liquid coming out, that's not gasoline, thankfully. That's water. Because water is one of the products of burning the gasoline. Now, this would be perfect combustion. There's no such thing as perfect in life. And so you have some other chemicals that are in the gasoline, and then you have not complete combustion. And so you'll form some other things, like carbon monoxide, because of not perfect combustion. But this would be the ideal case. Now let's get to the lecture we're supposed to be on, which includes that kind of topic. So today we're talking about organic chemistry. Now everybody's heard of organic, right? My wife buys organic foods. What does it mean when she's buying organic foods? Okay, not preservatives. What did you say? Not with bad chemicals. I'm glad you said bad, and not with chemicals, because of course there are chemicals in all the food we eat. So you just drank some water. That's chemical right there. Put chemicals in her mouth. Danger, danger. Organic. People have the general concept that organic food means healthy food. Now, there's a lot of research to say that organic food isn't more healthy than regular food that you buy, like organic vegetables are not healthier. There is a difference, though. In organic farming, you use only natural pesticides and fertilizers. So you're not using synthetic, that is, humans haven't synthesized these chemicals that all came from something natural. Of course, if it's natural, it doesn't mean it's healthy, right? As nightshade mushrooms are very natural, but if you eat them, you will very naturally die. So natural doesn't mean healthy, and some of the pesticides they use in organic farming are very toxic. But the research does show that you have about 1/3 as much toxic pesticides in organic vegetables and fruits than you do in the regular ones you buy at the supermarket. So in terms of nutrition, there's really no difference. But in terms of the harmful pesticides, you get more of them with your regular stuff. That's not exactly what we mean by organic in chemistry. Right? I did all that so that we can compare to organic in chemistry. Organic in chemistry means a carbon-containing chemical compound. So organic chemistry is the study of carbon-containing compounds. It's a pretty broad field. Now, it was at one time believed that the chemicals in life could only be produced by living things. But, it's been probably 100, 200 years ago or so, it was shown that you could synthesize urea. Now, why would you want to synthesize urea? I'm not sure. But you could synthesize urea in the lab. You did not have to have a living organism to make urea, which gets its name from exactly what you would think is a primary compound in urine. So that was startling, actually, to scientists, that you could have these molecules that are life-forming coming from something that wasn't living. It was thought before that you could only make these compounds necessary for life from living things. That actually plays strongly into ideas of creationism. We believe that life was only created by God, and life is given from God. You can't create life from non-life. That's a fundamental belief that I hold. I don't think we can create a living thing. We can put all the ingredients together for a living thing, but it won't be a living thing. That synthesizing organic compounds put a little chink in that argument for many people. So how many organic compounds do we have? You can see here over 13 million are known, and about 100,000 new ones are discovered every year. Now, I tend to think, the chemistry is, they've got all the chemicals out there, right? Well, they're discovering new ones all the time. Now, those ones they're discovering are not simple. They're not like CO and CO2. They're probably hundreds of atoms, but they're finding new ones. And so now we know that some of them are synthetic. That means man-made. And some of them are natural, made by nature. Now, if you are taking a pill, and the pill is something like, one of the things that Amy takes is L-lysine. Lysine is an amino acid. So she's taking an amino acid. Is it natural or is it synthetic? Is it going to make a difference to her body if it's natural or synthetic? Is her body going to care what the source of these chemicals was? No, her body doesn't care at all. It doesn't make any difference. If it's L-lysine, the only way we know of making L-lysine, the L means the left-hand version. We will see in just a couple slides that for many, many compounds, you have multiple ways you can make it. You can make a left-hand version, a right-hand version of this very complicated amino acid. And if you try to make it in the lab, you always get equal mixtures of the L and the R, the left-handed and the right-handed. But the body can only synthesize the left-handed part. The right-handed part the body can't use. One of the things that I think still points to a creator God, that we use only the left-handed versions of all of our molecules. And so to make the L-lysine, instead of it just being lysine to be L-lysine, that means that you had to start with something that was natural so that you could get the L. Once you have the natural L, you can synthesize from there to make more of it. So I'm sure the L-lysine she's eating is synthetic. It's not, harvested from animals or plants. It's probably synthesized in a lab, but it had to start from something living to get the left-hand version only. Okay, what's so special about organic chemistry? The biggest special thing about organic chemistry is that carbon makes very strong and stable covalent bonds. So here's just showing bond strengths for different elements bonded to themselves. And so carbon here, 347 kilojoules per mole. That's the strength in the bonds between two carbon atoms. Similar for nitrogen, you notice that's less than half of the bond strength. Oxygen is even less. Sulfur is a little bit higher than nitrogen and oxygen, but still well below carbon. If you look at sulfur on the periodic table, where does it fall? No, sulfur is S. So it's directly below oxygen. Right, the halogens is one further. It is like the chalogens or something, but I don't know of anyone who's ever called them that. So it's just under oxygen, so it behaves a lot like oxygen, sulfur does, but it does have stronger bonds, but not nearly as strong as those in carbon. That's one of the big reasons for carbon study. Another one is making chains. Sulfur makes a pretty long chain, a chain with 8 members long. And actually, you notice this is a cyclo chain. It's cyclic, goes in a circle. Carbon makes lots and lots and lots of chains of unimaginable lengths. So those chains are another thing that make it very interesting. Carbon makes a solid here, diamond. That's what diamond actually looks like for carbon atoms. That's the simple unit cell. It's not simple at all. It's what is it? Face-centered cubic with 2 bases or 3 bases or something like that. It's been a while since I studied the crystallography. Next, this is what we just talked about. Next, carbon atoms will easily form bonds with many other types of atoms so that we can make lots of combinations. You saw 13 or 1.3, no, what's 13? 13 million known compounds. It's a lot of compounds containing carbon. And hydrocarbons are really, really important. Hydrocarbons are things that are made up of carbon and hydrogen. So hydrogen, carbon, methane, the example we used in our homework problem, CH4, that's a hydrocarbon. Another homework problem had ethane, CH6, that's another hydrocarbon, just carbon and hydrogen atoms. And, you know, other things. There's lots of different variations. They're just carbon, hydrogen. So here are some examples. These are all pentane. They're all pentane. They all have pent means 5. Ane means they're all single bonds between the carbons. So pentane means we know we have 5 carbons and it's all single bonds between the carbons. But the first one, just called pentane, the carbons form a chain that's 5 members long. In the second one, isopentane, the second carbon atom has an extra carbon on it. And so if you look at the longest chain is only 4. And it has a carbon coming off of that second. So that's what isopentane is. And then we have neopentane. The neopentane, you see, has the third carbon, or excuse me, the second carbon has 2 extra carbons on it, which means that you have the center carbon with 4 carbons on it. 3 different ways of making pentane. They're called structural isomers because they have different structures, but they have the same chemical formula. So the isomer means it has the same formula. And I better not make it so you can't see the I. So isomer means you have the same formula. So all of these are 5 carbons and 12 hydrogens. So if you say C5H12, you have not specified exactly what it is because it could be any one of those 3. Now I wanted to do one more thing. We have 3 different diagrams showing the same thing. The left side has on top a picture showing where the atoms are. We never do that because that would take forever to try to draw and shade it. The one below shows all of the carbons and hydrogens. We hardly ever do that because it takes a lot of time to write all of those H's and C's. The bottom one means the same thing. What do we see in the bottom diagram? We just see 4 straight lines. Everywhere there's a kink in the line, there's a carbon. At the end of the line, there's a carbon. So anytime you have a change in the line, there's a carbon present. And then you're going to have hydrogen atoms to give you 4 bonds for each carbon. And so I can look at this and I can say this here only shows one thing bonded to it. So that's a carbon. Since it only shows one bond, it must have the last 3 are going to hydrogen. So it didn't show that. I had to interpret that. Now I go to the next one here. Well, actually, I'm going to skip one and go to here. I have a carbon there because there's a kink. It has how many bonds to that carbon shown? How many lines go away from that kink? 2. So 2 are shown. How many have to remain then? 2. So that means we have 2 hydrogens. And so you interpret, it's a shorthand way of writing it. So we get to this one, and again we see, okay, here's a kink. How many bonds are on that kink? 3. So how many hydrogens do we have? We have to have a total of 4 bonds. We have 3 taken, so how many are hydrogen? 1. This one here, the center hydrogen or center carbon is shown with 4 bonds. So how many hydrogens do we have? None. None, because it's going to form 4 bonds and it already has 4 shown. So we have no additional ones that we attribute to hydrogen. So when I was talking about octane, 1, 2, 3, 4, 5. 1, 2, 3. Yeah, that's octane. That's a lot quicker to write. But you can still interpret it as 1, 2, 3, 4, 5, 6, 7, 8 carbons. And then the hydrogens, the N ones have to have 3, all the rest have 2. And so you can add up and count the hydrogens. So that's a shorthand way of drawing our organic chemicals. So structural isomers, molecules that have the same molecular formula but different configurations. Configuration is how you connected the atoms. That's why it has configuration equals connectivity. Now we just looked at the pentane, and there were 3 different possible structural isomers. The next one, if you go from 5 carbons to 6 carbons, what would a prefix be for 6? You might get the wrong one because there's more than one prefix for 6. It's hex. So this is hexane. Next one. I hate to admit it. I'm sitting here thinking, I think it's septane, but I never use it. Heptane. Heptane. Heptane, okay. Well, this one we've talked about. Octane. And yeah, I don't even know the names beyond that. So let's, nonane, but decane. Dodecane is 20, I'm not sure. But you can see that by the time you get to octane, there are 18 different ways of configuring to make octane. So it gets more complicated. You get to 20 carbons. There's 366,000 ways of making a hydrocarbon with 20 carbons and 42 hydrogens. It suddenly doesn't seem so amazing that we have 13 million known organic compounds when you have over 1/3 of a million just in carbon 20, hydrogen 42. So we've already talked about this, this drawing. But this is not focusing on the drawing. It's something else. Conformation. If you conform, like the college has certain rules, if you conform to those rules, what have you done? You followed them. You have, and the way I want you to think about it here is, you have bent to fit into the college's rule system. Conformations are different ways of arranging the physical shape even when the bonds are the same. So if you look at these, each one has 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. But they don't look the same because this here has been changed in the direction it bends. That's actually a big deal. In our bodies, the shapes of proteins are fundamental to how our bodies operate. And so you can have different shapes to the proteins based on how they're bent. And that makes all the difference. And so, for instance, the L-lysine versus R-lysine. L-lysine helps my wife avoid cold sores. R-lysine would do nothing for her because it has the wrong shape. So this picture is indicating a difference in the bending. Now, what fundamentally makes that difference? Yes, this would have a hydrogen here and a hydrogen here, hydrogen here, hydrogen here, and of course, the 3 on the end I'm not going to show. This one here is bent around, so these hydrogens are both on the same side to make it bend. So that's what the difference is where the hydrogens are making it twist around. Okay, your first, and since we only have 2 minutes, last clicker question. Wow. One day I'll figure it out. What is the chemical formula for this structure?
I just feel like I click into one of my classes.
Oh, wait, Gabby. Okay, so we had 1, 2, 5, 0. Okay, that's a bit of success and a bit of failure. So, Samuel Reese, right? I know I've asked you multiple times, so I shouldn't have to ask you again. How do you determine how many carbons are present?
How many, line segments there are?
Okay, that's probably a better description than what I said. How many endings of the line segments? Because I said the end of a line or a kink. Ending of a line segment covers both, and it's one thing instead of two. So he counted how many ends of the line segments. So there was 1, 2, 3, 4, 5. So we can say right away that there were 5, but I'm going to stick with you, Sam. That's the only answer with 5 carbons. How do you know that it had 12 hydrogens?
Because the ones where it's not open-ended, you have to have 3, and the ones where there was another bond to it, you have to have 2.
Right. So you look at that and you just say, how many more hydrogens did I have to add each place because they're not shown? 3 if there's only an end. 2 if we had 2 meeting. If there had been 3 meeting, we would have added 1 and so on. And so he was able to come up with the 12 as well. Last thing for today is the gasoline that we use. Gasoline that we use is distilled. Now you guys have probably heard of a still, right? If you're from Kentucky or Tennessee, you might have one in your neighbor's backyard. A still is something that will heat up a material and have it go into vapor and then condense it. Why are stills used for alcohol? Because they make the alcohol, and alcohol goes into vapor at a lower temperature than things like water. So if you have a combination of water and alcohol and you boil it, you will have the alcohol and some water go into vapor, and then you cool it and the water will drop out first and you'll be left with alcohol, and then you collect the stuff that didn't drop out first, and that's going to be pure alcohol. So it's a way of purifying. So they do the same thing with oil. So you get your crude oil, stuff that you pump out of the ground, and then you heat it up. Now that is inherently dangerous, right? To heat up the crude oil so that it's all vaporized. If you get a little spark, boom, an explosion. And then you put it in this fractioning tower where the temperature gets cooler and cooler as it goes up. And different things will condense at different heights. So the stuff that never is fluid, that's tar, stuff we use in the road to patch holes. And then we have the stuff that we use for lubricants. It vaporized and recondensed when it got just a little bit cooler. Cooler still diesel, cooler still kerosene. The really coolest temperature where it still condenses is gasoline. Anything that doesn't condense is natural gas. So that's how they separate from the raw crude oil into the different grades that we use in life. All right, I'll see you tomorrow for lab. And we will have some continued